Okay, so we are going to continue from where we left off the other day. What I'm going to do is quickly once again go over the implementation of the biquad filter in a folded architecture, right? At least some parts of it, so that we can once again just review some of the decisions that were taken, how the architecture and how the choices of scheduling instance that we make translate into the hardware implementation. Okay, so to do that, I'm going to quickly just redraw the circuit that we started with. So the numbers that I'm writing up here are just identifying numbers for the different nodes. So I'll just call this node number 1, 2, 3 and 4. So in other words, nodes 1 to 4 are adders, 5, 6, 7 and 8 are multipliers. Okay, for the multipliers themselves, I'm showing only one input. The other input is a coefficient, and since that is constant, I'm not going to show that as a separate inputs, but of course all the 4 multipliers have different coefficients associated with them. Okay, so yeah, so the 4 multipliers have the labels that I'm giving to them are 5, 6, 7 and 8, and the coefficients I'm not indicating over here. We'll just use some variables to indicate them when necessary. Okay, there is an input which I will just denote by in over here, and an output that is out. You can call it x of n, y of n, it doesn't matter what exactly is the terminology you use there. And the next thing that is required over here is that I need to specify the folding schedule, right? The time instance or the phases at which the different operations are executed. Now, I think the numbers that I had given the last time around in class, there was some confusion regarding those. So please bear with me. The numbers that I'm giving now are what I'm going to use for the rest of the implementation. Okay. So the time instance are basically, I'm writing them down in red over here. This is at time 3. This is at time 1, 2 and 0. So in other words, we can see that there are 4 additions scheduled at the time instance 0, 1, 2 and 3, corresponding to 4 phases of the clock. Okay. Similarly, the multiplications are, this one is 0, this is 1, this is 2 and this is 3. Okay. So the red numbers, in other words, indicate the phase of clock for executing that operation. Okay. So what we have is n, the number of phases, is equal to 4. The folding sets themselves are S1 for the adder corresponds to operation number 4, then operation number 2, then operation number 3 and operation number 1. This is for the adder. And S2 is equal to 5, 8, 6 and 7 for the multiplier. Okay. So couple of things to again keep in mind over here. In this original diagram, this diagram that I've drawn over here, even though it is strictly not speaking a data flow graph, you need to be a little careful how you interpret it. The way that I have drawn it, it is not exactly a block diagram corresponding to a final architecture either, right? Because an architecture would actually mean that physically I have this many adders, this many multipliers, and so on. And what I'm drawing over here is with 4 adders, 4 multipliers, whereas what I'm saying is I'm trying to get an implementation that has only one hardware adder and one hardware multiplier. So this diagram is sort of closer to a data flow graph than a hardware block diagram in that sense. What it is showing is only the connections between the different nodes, the dependencies, and also how many delay elements, sample delays, are present on the edges that link different nodes. Okay, because of that you need to sort of interpret this a little bit carefully. What I mean by that is, so for example, this line that I have drawn in magenta over here corresponds to one edge in the data flow graph, right? This is the edge from node 1 to node 6 with the number of delay elements on it is equal to 1. This W is the number of sample delays. Okay. Similarly, I have another edge that goes over here from, this is an edge from node 1 to node 8, and it has W, the number of delay elements, equal to 2, right? Both of these delay elements, in other words, correspond to this magenta edge that I have drawn over here. Okay, so I have drawn it in this fashion so that it is compact and easy to sort of visualize what the structure looks like. But in order to actually interpret what are all the different edges that need to have implementations when you fold the architecture, you need to actually take what are the operational nodes, what are the adders, what are the additions that need to be done, what are the multiplications that need to be done, and find out the connections between them directly. How many sample delays are on those edges between them. Okay. Now, with this structure in mind, we then went forward and said I can now compute something called a DF value, right? And the DF value was essentially, it's something like what are the extra delays or the extra number of registers that are required in order to get the data correspondingly to the right input at the right time instant, right? To understand that a little bit better, let's take a couple of examples. I'll look at the edge from 1 to 2. Okay, this edge from 1 to 2 has W equal to 1. Okay, alright, so let's work through that. This has W equal to 1. The schedule time of operation number 1 is at time 3 and operation number 2 is at time 1. Okay, so this was scheduled at time 3, this was scheduled at time 1. Okay, so the DF therefore is the time when 2 was scheduled. Okay, or in other words, let me just write that out clearly. It is the time of operation number 2 minus the ending time of operation number 1, T1 plus PA, the pipeline latency of the adder. Okay, this plus N into the W. Okay, so in other words, it's equal to minus of 1 minus 3 plus 1 plus 4. Okay, or 4 minus 3 equal to 1. Okay, so I wrote it out in this fashion so that it becomes clear how I arrived at it, right? This T2 is the time when 2 is scheduled. T1 is the time when 1 is scheduled. T1 plus PA is the time when 1 completes and therefore its output is ready. Therefore, T2 minus T1 plus PA would be the extra number of, would be basically, so T1 plus PA is the time when 1 has finished. T2 is the time when that product, that value is then consumed. Okay, and if there are W delays, then T2 plus N into W is the time when it is consumed. Okay, T1 plus PA plus N into W is the time when it is consumed. Let me just get that clear. Yeah, sorry, there should not be a minus over here. Yeah, okay, so another way of looking at this is T1 is scheduled at, or rather operation 1 is scheduled at time T1, completes at T1 plus PA. Operation 2 is scheduled at T2. W delays correspond to N into W clock cycles. In other words, if I want to use the value produced by operation 1, W samples later, then that will correspond to the execution of T2 at T2 plus N into W, right? Okay, so the data that was produced at time T1 plus PA is going to be consumed at time T2 plus N into W. For that much intermediate time, I need to store that value. Okay, that is the number of extra physical registers that I will need to allocate somewhere to save the data until it is ready to be consumed, right? Which is what we have over here. The time of T2 was 1. This was 4 into 1 minus 3 plus 1. So it finally becomes equal to 1. Okay. The reason why I am working through this is I want to make sure that all of you understand how this was arrived at. Because finally what you will probably end up doing is just use a formula, right? Because after all, I can just simplify this formula and say that in general df from some node u to v is equal to time of v plus n into the number of delays between u to v minus tu plus pu. Okay, so in general you can compute the df value like this for any pair of nodes in the original graph, right? If we go back and look at this, I can pick any pair of nodes and write down the df value in this way and compute it. Okay, so let me just write that down for a couple of more edges just for clarity. So for example, we'll take let's for example take node number 2 itself, find the other element that is leading into it, which is basically an edge from 4 to 2. So df, in other words, from 4 to 2 will be equal to the execution time of the target 2 is time 1. The number of delays on the edge is 0. So 1 plus 4 into 0 minus 0, which is the time when operation number 4 is scheduled, plus the latency of operation 4, which is an adder. So df from 4 to 2 becomes equal to 0. Okay. So I'm not going to work through the rest of this. What I would suggest that you do is, I have already uploaded the link to Professor Parhi's website, where one of the slides for chapter number 6 actually contains the details of the exact implementation for this biquad filter structure, right? So what I'm going to do is just pull that up over here, right? And over here what we can see is that the folding equations for every one of the 11 edges has been drawn. Okay, so let's just go back here and look at this. There are 11 edges if you work through it, basically corresponding to each of the different inputs that we have coming in over here, right? So from 1 to 2, from 1 to 6, 1 to 5, 1 to 8, 1 to 7, etc. You work through it. Total number of edges are as seen over here. The df values for each and every one is computed. So df from 1 to 2, for example, is what we already did. We computed it to be equal to 1. df from 4 to 2, again we computed to be equal to 0. Right? So similarly you can compute df from 1 to 6, 1 to 8, etc. All the values can be done over here. How do you translate that into a hardware architecture? What's shown on top is basically what the hardware architecture looks like. Okay. So what we can see over here is, let me just so what we can see over here is that, let's take a look at operation number 2, for example, right? So operation number 2 is an addition, right? It occurs at time 1, phase 1 of the clock. So that means that I should basically be interested in what are the inputs coming to the adder at phase 1. Okay. I can see that this is one of them and this is the other one. Okay, so where are they coming from? This one is basically coming from the adder output over here, and this is coming from the adder output over here. Right? So what does that correspond to? If I go back and look at operation number 2, it had two input edges, one from 1 to 2, the other was from 4 to 2. So df from 1 to 2 had a df value of 1, and from 4 to 2 had a value of 0. Okay. So when I say that the df from 4 to 2 has a value of 0, essentially what I am saying is the input to 2, which is coming from 4, is to be taken from the output of my adder module with 0 additional registers after it. Okay, that is what this corresponds to, this line out here. Okay, this is the output of the adder. This is output of adder with 1 register delay. Right? So in other words, this corresponds to the edge from 4 to 2, and this corresponds to the edge from 1 to 2. Okay? Let's take another one of the example edges over here. Excuse me. Operation number 4. Okay? Operation number 4 is getting both its inputs from multipliers. Okay. In other words, the inputs to operation number 4 are coming from operation number 6 and from 8. Huh? Yes, but what I'm saying is, you remember what I said, this is just a data flow graph. When I say that it is getting its inputs from multipliers, what I mean is the functional unit. Huh? From 8 to 4. Oh yes, I'm sorry. Thank you for pointing that out. That's because I missed a register over here. Right? So yes, that is an important point. There is a register out here. Okay? Without that, the DF would have been negative and there would definitely be a problem. Okay? Thanks for pointing that out. So yes, the inputs to 4 are coming from 6 and from 8. Okay? The corresponding DF values, let's just simplify matters and go look at this. These are the two values that I'm interested in. Right? DF from 6 to 4 essentially corresponds to 0 minus 2 minus 2. So minus 4 plus the one sample delay over here. Right? So it basically becomes 4 minus 4 equal to 0. Okay? And on the other one, it basically becomes, this would start at time 1, end at time 3, plus one sample delay, so time 7, minus the time when this is scheduled. This would be required. This is at time 1. Yeah. So basically, this would be requiring the data at time 0 plus one delay over here, so that's at time 4, minus 1, which is the time when this is scheduled, minus 2, which is the pipeline latency of the multiplier, right? So if I work through this, what I'll find is that the DF for 8 to 4 comes out to be equal to 1, and from 6 to 4 works out to be equal to 0. So in terms of the hardware, what does that mean? It means that at what time instant was 4 scheduled? At time 0. So let's go look at the inputs to the adder at time 0. This is one, this is the other. Okay, where do those edges come from? This one basically comes with one extra register out here from the output of the multiplier, whereas this one comes directly from the output of the multiplier. Okay, so this, in other words, if I switch to this, corresponds to the edge from 6 to 4 with DF equal to 0, whereas this other one corresponds to the edge from 8 to 4 with DF equal to 1. Which is what I'm seeing over here. Okay, so the bottom line is this. Once I have shown you this architecture, you can then interpret it backwards in terms of the original design. But if you think about it, it is also not very hard to come up with this architecture, because once I have come up with all these DF values, what is the procedure that I should follow? First put down these two blocks, one adder, one multiplier. Okay, then put down the different phases 0, 1, 2, 3 for each of the inputs. Okay, at phase 0, what is the operation that's being executed on the adder? Find out where its inputs are coming from. Find out what are the DF values on those links. Put an appropriate number of registers to delay those links, and then connect them up to the appropriate phase. Okay, it turns out that in this case, the output of the adder, you might have to have up to 5 delay elements on it. That is because the maximum value of DF essentially corresponds to this value, 5. That's why I have 5 delays out here. Okay, and if I look at it, the DF values that are coming out from the multipliers, the max is basically 1, which is why I just have this 1 over here in one particular instance. or rather for two instances, for 0 and 2, time instance 0 and 2. Okay, so this should tell you that the procedure that you can follow in order to get a folded architecture is fairly straightforward, right? You start off with your data flow graph. You determine the different folding schedules at which time instance those different operations need to be scheduled. Is that a very trivial thing to do? Not exactly. That's exactly where we are going next. Okay, that's what we are going to be looking at after this. But it can be done. So assuming that I can come up with those folding orders, the next question is, how do I compute the DF values and how do I come up with the hardware architecture? That is more routine, fairly straightforward to do, right? I can basically put down a basic architecture, put down the number of registers after it, and make all the connections. Okay? If you think carefully about it, there are still a couple of tricks involved over here that are not very obvious, right? For example, if you look at this particular delay element, right? This register out here, it is basically the output of the multiplier being put through one register and then being provided as input to the adder at phase 0 as well as at phase 2. Right? Now the fact that I could use that particular register in order to do both of those was not entirely obvious from the original design. Okay, that I could share this particular register. In particular, if I had chosen to give this multiplier input to the other input of the adder at phase 2, right, I won't be able to share this register. I would have ended up needing two registers, or I would have had to do something else to my diagram over here. My diagram would have changed in some way. I might not have been able to share some of the wires at least. Okay, so there are some finer details that are involved over there that could further, result in minor modifications to your design, but not very significant ones. They would mostly be relatively small changes to the design that you end up with. Okay. So, to summarize, once I am able to come up with a set of folding orders, the folding schedule, the process of converting that into a hardware architecture is something that is reasonably automatable. When I say automatable, I can write a program to automatically create this structure once I give you the folding orders. Because what does that involve? It basically involves computing all the DF values and then making all the connections. That is something that computers are very good at, because there is a fixed procedure for doing it. You can write a program to do it and you can automate it, right? And that is one of the key takeaways from pretty much everything that we are trying to do in this course. What are the processes over here that can be automated, right? And if they can be automated, how well do they work? Okay. So the next thing, of course, that you need to keep in mind over here is, if it can be automated, why are you learning this? Right? After all, there is a compiler or a program that can do it for you. That's exactly the point of this course. You need to understand how the compilers work or how the programs work, so that you understand where the problems are and what it is that they are doing, so that if and when they don't give you the best possible design, you understand why and you can actually work around those, or you can improve upon them even further. Okay. Alright, so with that we are going to stop this aspect, which is essentially the study of how to obtain the hardware architecture, right, given a design. Which leads us to the next interesting question, which is, how did I come up with those folding numbers in the first place? Okay. So for this, we are going to take a step back and look at what the original biquad filter structure looked like, and not the form in which I showed it to you just now. Okay, what I mean is, the normal biquad filter structure that would be familiar to a person from the signal processing background would look something like this. right? This is essentially a second order or basically a biquad filter structure, right? It has two components. It has an IIR component as well as an FIR component. How did we obtain this? It essentially comes up from the structure of the normal, the y of n is equal to something y of n minus 1 plus something y of n minus 2 plus something x of n minus 1 plus something x of n minus 2, right? But if you look at it, it's a bit more tricky than that, because what has happened over here is the IIR portion, the feedback, is in the left hand side, the earlier part of the diagram, and the feed forward is in the later part, right? It turns out that this is most easy to understand if you look at it in terms of the signal flow graph and do that transposition operation that I had mentioned somewhere in the earlier while we were talking about signal flow graphs, right? That's the easiest way to sort of obtain this structure, right? But how we obtain it, why it works, why it is used, etc., is not our concern. As far as we are concerned, the reason why we take it up is it is a very common structure in several kinds of signal processing applications, primarily related to speech and other kinds of things, but also it has certain properties that make it a very stable and useful basic component of signal processing hardware implementations, right? And as far as we are concerned, it gives us a very nice simple structure that allows us to experiment with different kinds of, or rather allows us to understand the different kinds of scheduling algorithms easily. Okay, so once again I'm just going to label these nodes 1, 2, 3, 4, 5, 6, 7, 8, right? And you can see that the difference between this and the diagram that we used earlier is simply this: the positions of those delay elements or registers is different. Okay, why did I have to make those changes? Why those specific positions? Were they important, or could I just have placed them anywhere? That's what we are trying to understand now. Okay, so to figure this out and to sort of see how do I come up with a schedule, right? We would like to essentially understand what are the real dependencies that I have over here, and how would I systematically go about constructing a possible schedule of operations on limited amounts of hardware if I had to do that. Okay, so what am I dealing with? Let's take a look at this. Based on what I have over here, right, I'm just going to ask a few questions. Let's say that n is equal to 4 as before. Okay, the question that I'm going to ask is 0 acceptable as a scheduling time instant for operation number 1? Or, so what would you say if I asked you that? Is 0 acceptable as a scheduling time instant for operation number 1 as it stands right now? No. Why? Because there is a dependency from 3 to 1. Therefore, 3 has to complete before 1 can execute. There are no delays on the edge between 3 to 1. That's all that I care about. Right? I only care about the edge between 3 to 1 right now. There are no delays on that edge. Therefore, the only possible way that 1 could execute at time 0 is that 3 has a negative schedule instant, which is not possible. Okay? This would force operation 3 to execute at negative time. Okay, so clearly 0 is not possible. The next question I can ask is 1 possible? At least if operation 1 is to execute at time instant 1, what would that imply for operation 3? It has to be at 0. What does that imply for operation 5? It would have to be negative, which again is not possible. Okay, so therefore 1 is also not okay, because this would imply 0, this would imply this becomes negative. So that's also not okay. Now, what about operation 5 executing at time 0? Is that okay? Do you see any problem with operation 5 executing at time 0? Huh? Operation 2 would have a problem. Okay, so now let's work through this, right? If operation 5 is scheduled at t equal to 0, what would it mean? Operation 3 has to be at t equal to, it has to wait till 5 completes, and 5 is a multiplication. So the latency of multiplication is 2 clock cycles. 2. That's the earliest time that operation 3 can execute. I should put greater than or equal to, but I'm just going to put equal to over here. Operation 1 therefore can execute at time 3, right? Which in turn means operation 2 at time 4, and this is a problem. This is not possible if n is equal to 4. Okay, and in fact this is raising a fundamental problem for us, because if I really look at it, what is happening over here is there is a path that leads over here which has a length, a total delay length of 2 plus 1 plus 1 plus 1, 5 time units. So there is fundamentally no way that I can get everything to finish within 4 clock cycles with this arrangement. Okay, and in fact, what is the name that I normally give to this path? The critical path, right? What it's saying is, in this diagram as it stands over here, the critical path is 5 time units long. So n equal to 4 is basically not possible since the critical path is equal to 5 time units. Okay, so what do we do? Let's assume n equal to 5. Okay, so what does this correspond to? I'm just going to put down a time chart over here, right, where I put t is equal to 0, 1, 2, 3 and 4, and put down the operations over here, right? Let's go back and look at this. What I can see is operation 5 can be run at time equal to 0. No problem with that. Okay. That would imply operation 3 can be at time 2. Okay, so I'm going to put an arrow between them to indicate that there is a dependency over here. Operation 1 at time 3 and operation 2 at time 4. Okay, what about the rest of my dependencies? So that is basically, that has taken care of this path 5, 3, 1, 2. Okay, all right. What about operation 6? That can also execute at time 0. Actually, yeah. That in turn feeds into operation number 4. and that in turn feeds into operation number 2. Okay, what about the other operations? So I have 7, which again feeds into 3. Okay, so the output of 7 again has no input dependencies because it has a delay element in front of it. So what that basically means is anything which has a delay element in front of it, the input corresponding to that could have executed in the previous iteration. Okay, so in this particular block, the schedule that I'm trying to put down for these 5 phases, right? 5 has no dependencies, 6 has no dependencies, 7 has no input dependencies, and 8 has no input dependencies. Okay, and if you look through it, what you will find is 7 is also here, 8 is over here. Okay, this is the set of dependencies that I have got right now. Okay, what you can see from this is this or this, either one of those is a critical path. Right, whereas this one over here is not a critical path. Okay, so you see the difference between those two paths. The 642 and the 842 also terminate on 2, but they are not critical in the sense that the output of 4 was ready by time 3. Okay, so how does that help us? Potentially what I could have done is to have a slightly different schedule which could have basically allowed me to sort of push this down. So 6, in other words, could have gone here, 8 could have gone here, and 4 could have gone here, and I would have still met my timing constraint. Okay, so the paths that are not directly on the nodes that are not directly on the critical path, in other words, could be moved around a little bit. Okay, I am anticipating a little bit over here. This is essentially the same as the concept of slack in a digital combinational circuit, right? There is some slack on this path, whereas on the 5312 path or the 7312 path, there is no slack. They are exactly critical. The others have slack. They have some amount of mobility. Okay, so how does this help us? If I was to say n is equal to 5, let's go one step further and say, is that good enough? If I just said n is equal to 5, now can I get a hardware architecture where I can just use one multiplier and one adder and get all my operations done? Yes or no? Will I be able to manage with one multiplier and one adder? Still not going to work because I have 2 multipliers sitting at time instant 0 on my critical path. They can't be moved. In my original schedule, of course, the one that is written in black, 5, 7, 6 and 8, all the multipliers are scheduled at time 0. The only way I can do that is use 4 separate multipliers. Okay, so as things stand right now, with my original schedule, 5, 6, 7, 8 are all scheduled at time 0. I need 4 multipliers. Okay, what I have drawn there has a specific name. It is something called the ASAP schedule. What does ASAP stand for? As soon as possible. Okay. So the ASAP schedule for this filter structure that we have over here essentially corresponds to, in what's the simplest way to obtain it? Take any edge that has a delay element on it, delete it from the graph, right? once I have deleted all edges that have delays on them, I can guarantee that the resulting graph cannot have any cycles. That was pretty much my starting point, right? My iteration period bound and the fact that I cannot have combinational loops, etc. All of those things intuitively, I know why any loop or a cycle in this structure, the graph that I have, must have at least one delay element on it. So if I delete all edges that have delay elements on them, the resulting graph will not have any cycles. It becomes something called a directed acyclic graph. Okay, and in this case the directed acyclic graph essentially looks like the set of operations that I have over here. I have 5 and 3, 5 and 7 feeding into 3, the output of 3 feeding into 1, which in turn feeds into 2. Okay, and I have 6 and 8 feeding into 4, which in turn feeds into 2. Okay, this is just the directed acyclic graph. It does not necessarily talk about how much time each operation takes to execute. But once I have this directed acyclic graph, I can use it to straight away draw an equivalent as soon as possible schedule. As soon as possible, as the name implies, means every operation executes at the earliest time instant possible. So what would the ASAP schedule for this look like? Five and 7 would be over here. They would then essentially run for this long, 2 clock cycles. The output of that would be used by 3. The output of that would be used by 1. And the output of that would be used by 2. Okay, similarly 6 and 8 would also be scheduled at time 0, that is the earliest possible time when they can be scheduled. Immediately after that would come 4, and that would then feed into 2. Okay, so this schedule where I have 4 multiplications all scheduled at time 0, 2 additions scheduled at time 2, and one addition each scheduled at time 3 and 4 is the so-called as soon as possible schedule. From a hardware point of view, it's bad. I mean, it looks bad because I basically need 4 multipliers and 2 adders, right, in order to realize this hardware. Whereas I know that I can actually implement this using 1 multiplier and 1 adder. Okay, so can I come up with something better? How do I improve upon it? How do I modify this? Those are the questions that we are going to address next. Okay, so we'll stop here for now. Tomorrow we'll continue with this, look at the basics of as soon as possible scheduling, switch over to as late as possible scheduling, how we can move that around, and also see what kind of changes we need to make to the original graph so that it can be scheduled within 4 time steps, and then we can actually meet our constraints. Okay, all right.